This energy signature of the nascent universe comes to us by way of 13.7 billion years of cosmic evolution, not to be mistaken for biological evolution. Recall that universal expansion has stretched light coming at us from distant sources. The afterglow of the Big Bang, being the most distant of these sources, has undergone a vastly larger lengthening of its wavelength, well past the visible spectrum and into the microwave range, hence the name cosmic microwave background radiation. If this afterglow has truly been traveling for some 13.7 billion years, then its temperature today is expected to be roughly 3 degrees Kelvin. That's 3 degrees above absolute zero. Unsurprisingly, analyses of the cosmic microwave background radiation corroborate this finding. Another prediction about the afterglow of the Big Bang is that it must have a black body spectrum. So what is a black body? This is a black body. Well, not entirely, but it'll have to do for now. The internet is full of delightful surprises, even when one is honestly just looking for black body spectrum. Now then, why are the undergarments of this young lady black? I will give you some time to think about it. Feel free to inspect her undergarments closely. Alright, time is up. The undergarments of this fine lady appear black because they absorb all the incident light within the visible spectrum. A true black body, however, absorbs all incident light from the full electromagnetic spectrum. Say goodbye to the lady now. If the black body is then heated to a constant temperature, it will release black body radiation, and this radiation, or light, will display a specific curve given the temperature to which it has been heated. Notice the temperatures and their associated curves on this diagram. Recall that the early universe, with its thick plasma, imprisoned all the light. Therefore, in principle, the afterglow of the Big Bang should have the sort of spectrum we would expect to see in a black body. And, lo and behold, it does. Not only does the cosmic microwave background radiation produce the kind of black body spectrum that we would expect to see at 3 degrees Kelvin, but also it is nature's best example of such a phenomenon. This diagram shows the relation between the observed spectrum of the afterglow and the expected black body spectrum at 3 degrees Kelvin. It should be noted that in science, it is extremely uncommon to see such quasi-perfect merger between observation and prediction, and yet here, this is exactly what we have. Given all the independent lines of evidence that we have considered thus far, and there are more, we can be reasonably sure as we can be in science, that the Big Bang did indeed happen. Even so, there is still a lot that we simply do not know, and our standard Big Bang model does have its own share of shortcomings, like any other scientific model or theory for that matter. The cosmic microwave background radiation, the single most important evidence in support of the Big Bang, turned out to be somewhat of a double-edged sword. Why? Because its temperature is unbelievably uniform, with variations only perceivable at the part per million level, and this brings us to the horizon problem. Variations in the afterglow of the Big Bang are directly related to variations in the matter density of the early universe. The fact that the cosmic microwave background radiation is so homogeneous therefore entails that the early universe had an equally uniform matter density, and this is a problem. Information cannot travel faster than the speed of light. At best, it can only travel as fast. Consider these 2 points, A and B. The distance separating them is denoted by x. If point B can receive light from point A and vice versa, then points A and B are said to be in causal contact. In other words, points A and B can share information. If we increase this distance enough, now denoted by y, we find that light produced by A has not yet had the time to reach B. The opposite is also true. In other words, points A and B cannot share information. The maximum distance physically allowed for the exchange of light and therefore information to occur between points A and B is known as the particle horizon. In this schema, points A and B can share information, but beyond the particle horizon will no longer be able to do so. Think back to what we had said about the afterglow of the Big Bang coming at us from all directions, and consider this figure. In the center, we have the Earth, encompassed by the observable universe. The thin arrows represent the cosmic microwave background radiation reaching the Earth from every direction. Galaxy A and Galaxy B are also sending light towards the Earth. However, given the age of the universe, galaxies A and B have not yet had enough time to receive light from each other and, thus, are not in causal contact. Basically, galaxies A and B are visible to us here on Earth, but they are mutually invisible. What can be said about the surface from which the afterglow of the Big Bang is reaching us? Well, the same principle of causal contact applies here too. If we were to draw an angle of 2 degrees at the position of the Earth, the arc that would be produced at this very surface would correspond to the particle horizon of the early universe. It follows that points separated by distances greater than this particle horizon would not be in causal contact. This causal independence between such points would entail that the cosmic microwave background radiation be irregular, and yet, as noted earlier, it is anything but irregular. It is strangely uniform. This is the horizon problem, figuring out just how the early universe could have produced such a uniform afterglow. Physicists huffed and puffed, and finally developed a concept that would explain the uniformity of the cosmic microwave background radiation without having to change the fundamentals of the Big Bang. They called this new idea inflation.